This is Linear Algebra, Lecture 14. And I'm just going to review some of the more recent topics that we covered that are on the final. And the most important is eigenvalues and eigenvectors. So we have, let's say, a matrix A, an n by n matrix, Aij, and a vector x is an eigenvector for A with eigenvalue lambda if first x is not the zero vector and ax is lambda x. And so if x is an eigenvector, then the one-dimensional subspace in Rn, consisting of just all scalar multiples of x, is invariant under A. And we use interchangeably the language of matrices and linear transformations. If you have any linear transformation from an n-dimensional vector space to itself, dimension of V equals n, then there's a certain matrix with if you take a basis for V, the linear transformation T has the matrix A, an n by n matrix, and which operates by ax, T of x is ax. And the one big theorem says that if A is a real symmetric matrix, symmetric means the transpose of A equals A, then there is an orthonormal basis of eigenvectors for the vector space V, or Rn in this case. And we consider the special case n equals 2. So A is a 2 by 2 matrix, which I'll often write as just A, B, C, D. And if it's symmetric, that means A is A, B, B, D. Symmetric means the transpose of the matrix is the matrix, so these two numbers have to be the same. So let's take an example. Suppose I let A be the 2 by 2 matrix 3, 2, 2, 4. So we already know that this is just sort of the general theory. If A is the matrix A, B, C, D in general, an arbitrary 2 by 2 matrix, lambda is an eigenvalue of A if and only if lambda is a root of the quadratic equation lambda squared minus A plus D lambda plus AD minus BC equals 0. So what is the quadratic equation in this case? Because in this case, A is 3, B and C are 2, and D is 4. So lambda squared minus A plus D is 7, plus AD minus BC, that's 12 minus 4 equals 0. So lambda is going to be a root of this quadratic equation, and we know the quadratic formula. So lambda is minus b plus or minus the square root of, so b squared minus 4ac for this quadratic. That's 49 minus 32 over 2. So this is 7 plus or minus the square root of 17 over 2. So we have two eigenvalues. Lambda 1 is 7 plus root 17 over 2. And lambda 2 is 7 minus root 17 over 2. So for each of these eigenvalues, we want to find an eigenvector. And from those eigenvectors, we want to obtain an orthonormal basis. A basis where each eigenvector in the basis has length 1, and the two eigenvectors are orthogonal. Their inner product is 0. So let's look for an eigenvector for lambda 1. So let's see, xy, let me call this v1. v1 is an eigenvector with eigenvalue. Lambda 1 means if I take the matrix 3, 2, 2, 4 applied to the vector xy, that's equal to lambda 1 times xy, or seven plus root 17 over 2 times xy. So we end up having to solve two equations and two unknowns. This matrix times this vector is 3x plus 2y. And that has to equal 7 plus root 17 over 2x. And 2x plus 4y has to equal 7 plus root 17 over 2y. So this equation is the same as I bring the x over to the other side. 2y equals this minus 3x, which is 1 plus root 17 over 2x, or y is 1 plus root 17 over 4x. This equation should have the same solution. Let's see, this says that 4y is 7 plus root 17. Sorry. This says if I take 4y minus this, 4 minus 7 halves is a half. So I get 1 minus root 17 say this in a better way. This says that this minus this, so 4y minus 7 plus root 17 over 2y. What is that? 4 minus 7 halves is 1 half. This is 1 minus root 17 over 2y equals minus 2x. So this says that if I solve this for y, I should get the same equation. Y is equal to minus 4x over 1 minus root 17. If I multiply this by 1 in the form of 1 plus root 17 over 1 plus root 17, this is 1 minus 17. I get minus 4, 1 plus root 17 over minus 16. The minuses cancel. This is over 4 times x. We get exactly the same thing. So for an eigenvector, I can let V1 be for any value of x, y is 1 plus root 17 over 4 times x. If I write this as x over 4 times 4, this is x over 4 times 4, 1 plus root 17. X over 4 is any scalar. So let me just call this V1 tilde. So V1 tilde, 4, 1 plus root 17. This is an eigenvector with eigenvalue lambda 1. So let me just summarize this over here. We have the matrix A, which is 3, 2, 2, 4. And we have eigenvalues lambda 1 equal to 7 plus root 17 over 2, and 7 minus root 17 over 2. And I claim that the vector V1 tilde 4, 1 plus root 17 is an eigenvector with eigenvalue lambda 1. So let's check. This is just a calculation we have to do. So A times vector V1 tilde, that's 3, 2, 2, 4, times the vector, which is 4, 1 plus root 17. This is 12, 3 times 4, plus 2 times this. 12 plus 2 is 14, plus 2 root 17 is the x coordinate. And 8 plus 4 times this is 12, plus 4 root 17. Let's see, what is that? This is, I have 14 plus 2 root 17. If I multiply and divide by 4, it's the same thing. And here I have 12 plus 4 root 17. Let me just check what this is going to be. So this is 14 plus 2 root 17 over 4. That's 7 plus root 17 over 2 times 4. And here, I want to say this is going to be something. Let's call it some number C. I hope it's C times 1 plus root 17. So 12 plus 4 root 17. So if 12 plus 4 root 17 is C times 1 plus root 17, C is equal to 12 plus 4 root 17 over 1 plus root 17. Then we multiply this by 1 minus root 17. In the denominator, I get 1 minus 17, which is minus 16. In the numerator, I get 12 minus 4 times 17 plus 4 root 17 minus 12 root 17. So 12 minus 4 times 17, that's 68. So this is minus 56 minus 8 root 17 over minus 16. Divide by minus 8, I get 7 plus root 17 over 2. So this is actually 7 plus root 17 over 2 times 1 plus root 17. So this is just 7 plus root 17 over 2 times the vector 4, 1 plus root 17, This is exactly that first eigenvalue, lambda 1, and this is v1 tilde. So this is a check that this vector v1 tilde is an eigenvector for this matrix with eigenvalue lambda 1. Now, what is the length of v1 tilde? The length of a vector is the square root of the sum of the squares of the coordinates. So that's square root of 4 plus 1 plus root 17 squared. That's the square root of 4 plus 1 plus 2 root 17 plus 17. That's the square root of 22 plus 2 root 17. It's not the prettiest number, but it's some number. It's certainly not equal to 1. Sorry, v1 tilde is 4 squared. v1 has coordinates 4 and 1 plus root 17. So the sum of the squares of the coordinates 4 squared plus 1 plus root 17 squared. So this is 16 plus 1 plus 17 plus 2 root 17. So let me do my arithmetic correctly. That's always an advantage. So this is 17 plus 17. This is 2 times 17 plus 2 times the square root of 17. Whatever it is, that's what it is. That's the length of the vector. So if I let v1 be equal to this vector v1 tilde divided by the length of v1 tilde, this is now a unit vector. So we just found one eigenvector for this linear transformation. What about the second eigenvector? The second eigenvector was lambda 2 equal to 7 minus root 17 over 2. So we want to find a vector xy, so that v2 tilde be xy. We want to find this vector v2 tilde such that a v2 tilde is lambda 2 times v2 tilde, or 3, what was my matrix? 3, 2, 2, 4 times xy, that's a v2 tilde, which is 3x plus 2y, 2x plus 4y, is equal to lambda 2. Lambda 2 is 7 minus root 17 over 2 times the vector xy. So this is 7 minus root 17 over 2x, 7 minus root 17 over 2y. It's that vector. So I have to satisfy the system of equations. The first equation is 3x plus 2y equals 7 minus root 17 over 2x, which is the same as 2y equals this minus this, which is 1 minus root 17 over 2x, or y is this over 4. So my vector xy, for any x, this is 1 minus root 17 over 4x. I can write this again. I think this is 4 times x over 4. If I take out an x over 4, it's that number times the vector 4, 1 minus the square root of 17. So suppose I let v2 tilde before 1 minus the square root of 17. Let's check. It's easy to make a lot of mistakes. So I have the second eigenvector, lambda 2, is 7 minus root 17 over 2. So I want the matrix times xy to be the scalar times xy. So 3x plus 2y is 7 minus root 17 over 2x. Or 2y is this minus 3x, which is 6 over 2x. So I get 2y is 1 minus root 17 over 4 over 2x. Divide by 2. Y is 1 minus root 17 over 4x. So for any x, 1 minus root 17 over 4x is some scalar multiple of 4, 1 minus root 17. So let me check. 3, 2, 2, 4. Apply to the vector 4, 1 minus root 17. This is 12 plus 2 minus root 17, 8 plus 4 minus 4 root 17. This was my eigenvalue, lambda 2. Let's see. If I take 14 minus root 17 over 4, that's 7. 12 plus 2 is 14 minus 2 root 17. 14 minus 2 root 17 over 4 is 7 minus root 17 over 2 is lambda 1. That was lambda 1 is this number. So this 14 minus 2 root 17 is lambda 1 times 4. 12 minus 4 root 17 over 1 minus root 17. What is that? This is 12 minus 4 root 17. I want this to be some multiple of 1 minus the square root of 17. So this is 12 minus 4 root 17 over 1 minus root 17. It's multiplied top and bottom by 1 plus root 17. In the denominator, then we get minus 16. We get 1 minus 17, which is minus 16. In the numerator, we get 12 minus 4 times 17. That's 12 minus 68. That's minus 56. And I get 2 root 17 minus 4 root 17 minus, this is correct, no, sorry, 12 root 17 minus 4 root 17. 12 minus 4 is 8 root 17. Divide everything by minus 8. This is 7 plus root 17 over 2. Let's see, I think I have the sign wrong somewhere. So I have 12 minus 68 is minus 56. I have 12 root 17 minus 4 is plus. So this, if I divide by minus 8, is 7 minus 2 root 7, 7 minus root 17 over 2, which is lambda 1. So this is equal to lambda 1 times 1 minus root 17. So this is lambda 1 times the vector for 1 minus root 17. And this is good. This is the check that this is lambda 2. This is a check that this is an eigenvector with eigenvalue lambda 2. So what are these what are the two eigenvectors that we computed before we normalized their lengths? We had v1 tilde is equal to four 1 minus root 17. v2 tilde, that's what I just calculated, is, sorry, the first eigenvector was 4 over 1 plus root 17. The second eigenvector was 4, 1 minus root 17. Let's compute the inner product. v1 tilde comma v2 tilde. That's the product of their first coordinates, 4 times 4, minus the product of their second coordinates, 1 plus root 17, 1 minus root 17. 4 times 4 is 16. 1 plus root 17 times 1 minus root 17 is 1 minus 17. 16 plus 1 minus 17 is 0. So v1 tilde, v2 tilde are orthogonal. And if you take each of these vectors and divide by their lengths, then these vectors are orthonormal. Orthonormal means orthogonal plus the vectors each have length 1. So this is an orthonormal basis of eigenvectors. And the whole point is to understand and simplify a linear transformation. So we have the linear transformation T from R2 to R2 defined by T of xy is 3, 2, 2, 4 applied to the vector xy, where this matrix 3, 2, 2, 4 is the matrix for the linear operator T with respect to the standard basis for R2. E1 equal to 1, 0, E2 equal to 0, 1. But we have a new basis, B, consisting of these orthonormal vectors V1 and V2, and the basis for the linear operator T with respect to this new basis B is diagonal. And what we have down the diagonal are the two eigenvalues. So the first eigenvalue is 7 plus root 17 over 2, 0, 0. 7 minus root 17 over 2. We have a diagonal matrix. So we have two vectors in the plane, and their directions are preserved by this linear transformation. An eigenvector with respect to a linear transformation is a vector such that the transformation times the vector just stretches the vector by a certain amount. It's a scalar multiple of the vector. So that's pretty good. So this is the fundamental problem about diagonalizing 2 by 2 matrix. It is 100% certain that such a problem or such problems will be on the final exam tomorrow. Okay, let's see. So it's not a coincidence that the eigenvectors for this matrix are linearly independent and orthonormal. We're talking about. So, but those are two separate phenomena. So let me just describe this in general. Suppose that T from V to V be a linear operator. Now, some linear operators have no eigenvectors or eigenvalues. To be a linear operator on a real finite dimensional vector space. Say dimension of V is equal to n. Let lambda 1 and lambda 2 be distinct eigenvalues for T. Distinct means they're different. Lambda 1 is different from lambda 2. Let V1 and V2 be eigenvectors for lambda 1 and lambda 2, respectively. That means that T of V1 is lambda 1 V1, and T of V2 is lambda 2 V2. Then, so we know eigenvectors are, by definition, non-zero. V1 is not the zero vector, V2 is not the zero vector. An eigenvector is defined to be a non-zero vector with some additional property. Then V1 and V2 are linearly independent. Why is that? Well, let's see. Why are they linearly independent? So suppose we have C1, C2 scalars such that C1, V1 plus C2, V2 is 0. Must show C1 and C2 are in fact both equal to 0. That's what it means to be linearly independent. So if C1, V1 plus C2, V2 is 0, T of the 0 vector is always the 0 vector. So, but the 0 vector is C1, V1 plus C2, V2. And by linearity, this is C1 T of V1 plus C2 T of V2. T of V1 is lambda 1 V1. T of V2 is lambda 2 V2. So we have this equation. We also have this. Suppose I take this equation, I just multiply it by lambda 1. If I multiply this by lambda 1, I get 0. Multiply the 0 vector by any scale, we're still 0. You get C1 lambda 1 V1 plus C2 lambda 1 V2. So I have these two equations. Subtract. When you subtract, these cancel. I get C2 lambda 2 minus lambda 1 V2 is the 0 vector. Now, V2 is not the 0 vector. It's an eigenvector, so we know it's not 0. Lambda 2 minus lambda 1 is not 0, because lambda 2 is different from lambda 1. So I have a scalar times a non-zero vector equal to 0. that means C2 has to equal 0. If C2 is 0, then C1 V1 is 0. V1 is non-zero, so C1 is 0. So if you have eigenvectors associated, if you have two eigenvectors associated with two distinct eigenvalues, they're linearly independent. Let's see if we can generalize this. Let's take the next simplest case. So we have lambda 1, lambda 2, lambda 3, pairwise distinct eigenvalues with eigenvectors v1, v2, v3. Suppose some linear combination of the eigenvectors is 0. Then T of C1, V1 plus C2, V2 plus C3, V3 is C1T of V1 plus C2T of V2 plus C3T of V3. But the V's are eigenvectors. So this is C1 lambda 1 V1 plus C2 lambda 2 V2 plus C3 lambda 3 V3. And that's T of this. That's T of 0, which is 0. So we have this equation. Let me just interchange the lambdas and the C's. Lambda 1 C1 V1 plus lambda 2 C2 V2 plus lambda 3 C3 V3 equals the 0 vector. But I also had my initial relation. Suppose I multiply this equation by lambda 3. If I multiply this by lambda 3, I get lambda 3 C1 V1 plus lambda 3 C2 V2 plus lambda 3 C3 V3 equals 0. These two terms are the same. If I subtract, I get lambda 1 minus lambda 3 C3 V1 plus lambda 2 minus lambda 3 C2 V2, and this minus this is 0 is 0. So what I have is a linear combination of V1 and V2. But V1 and V2 are eigenvectors with distinct eigenvalues, lambda 1 and lambda 2. So what we're multiplying, so they're linearly independent. So lambda 1 minus lambda 3, C1 has to be 0. And lambda 2 minus lambda 3, C2 has to be 0. But these numbers are different from 0. Lambda 1 and lambda 3 are different. Lambda 2 and lambda 3 are different. These are non-zero. So C1 and C2 have to be 0. But if C1 and C2 are 0, C3 V3 is 0. So C3 is 0. So these three vectors are three eigenvectors with distinct eigenvalues are linearly independent. And this generalizes if you have any finite number of distinct eigenvalues for a matrix or for a linear operator, and you take eigenvectors for each of those distinct eigenvalues, that set of eigenvectors is linearly independent. What about mutually orthogonal or perpendicular? So in general, that's not necessarily the case, but in the very special case, which is important in many applications, that's the case when A is a symmetric matrix. So A equals A transpose. When you interchange the rows and columns, you get exactly the same thing. If A is given by the matrix Aij, symmetric means that the entry on the ith row, jth column is the entry on the jth row, ith column for all ij going from 1 up to n. That's what symmetric means. And if A is symmetric, then it has the following very beautiful property. For all vectors v and w in my vector space, let's say Rn, if I apply A to the v and take the inner product with w, that's the same as the inner product of v with AW. So you can sort of move this linear transformation of this matrix from left to right or right to left in this inner product formula. The inner product of AV with W is the same as the inner product of V with AW. And the fact about symmetric matrices says the following. If A is a symmetric matrix and V1 and V2 are eigenvectors with distinct eigenvalues, lambda 1 and lambda 2, then V1 and V2 are orthogonal or perpendicular, or equivalently, the inner product of V1 and V2 is 0. So I want to show if we have a symmetric matrix or a symmetric linear operator, eigenvectors with distinct eigenvalues are orthogonal to each other. So let's look at, this is what I want to prove. So I have, let's say I look at AV1 inner product with V2. AV1, V1 is an eigenvector with eigenvalue lambda 1. So this is lambda 1 V1 inner product with V2. I can take the lambda 1 outside. That's lambda 1 inner product with V1 and V2. On the other hand, because A is symmetric, the inner product of AV1 with V2 is the inner product of V1 with AV2. And AV2, because V2 is an eigenvector with eigenvalue lambda 2, this is lambda 2 V2. I can take the lambda 2 outside, so lambda 2 V1 V2. So this equals this. Let me write it down. Lambda 1 V1 V2 equals lambda 2 V1 V2. So two things are equal. When you subtract, you get 0. If I take this minus this, I get lambda 2 minus lambda 1 V1 V2 equals 0. So this number times this number is 0. But lambda 2 minus lambda 1 isn't 0 because lambda 1 and lambda 2 are different. So if a product of two numbers is 0 and one is non-zero, then the other has to be 0. And the other number is the inner product of V1 and V2, and that's 0. So when you have a symmetric matrix, eigenvectors with distinct eigenvalues are automatically orthogonal. And why is it the case? This is the fact that I use. I use the fact that if A is symmetric, the inner product of AV with W is the inner product of B with AW. So let me prove that. It's something nice to know. So I'll prove a more general result. So suppose we let T from V to V be a linear operator and let dimension of V equal to N, let A equal Aij be the N by N matrix for T with respect to the standard basis, or the N by N matrix for T with respect to some orthonormal basis, E1 up to En. Orthonormal basis means that the inner product of EI and EJ is delta IJ, the Kronecker delta, which is 1 if I equals J, and 0 if I is not equal to J. We've seen that many, many times. So let B be the transpose of A. So let's say B has coordinates Bij, where Bij is Aji. So I'm not assuming that A is symmetric. I'm just letting A be any N by N matrix, and B is its transpose. And I claim, so this is a theorem, that A times any vector V inner product with W is the same as V inner product with B times W, or A transpose times W. And to prove this, it's enough to prove this for basis vectors, so proof. So it suffices to prove that AEI or AEJ inner product with EK is equal to the inner product of EJ with B of EK for all JK going from 1 up to N. So the way to do that is just do this computation. What is the inner product of AEJ with EK? So the A applied to EJ is summation A I J E sub I goes from 1 up to N. Inner product with AK, this is summation I goes from 1 up to N. Aij, inner product EI EK. This is delta IK. This is 0 unless I is equal to K. When I equals K, this is 1. So this is just when I equals K, this is AKJ. AKJ is the same as BJK. B is the transpose of A. What is the inner product of EJ with B times EK? That's the inner product of EJ. BEK is summation BIK E sub I goes from 1 up to N. This is summation I goes from 1 up to N. BIK, inner product of EJ and EI. Again, this is, sorry, yeah, this is right. Again, this is delta ij. This is 0 unless I equals j. When I equals j, this is 1. So you get bjk, which is this. So I just proved this relation on an orthonormal basis. And if you take any vectors v and w, let me actually just write this out because it's good to see every now and then. So I have B is equal to A transpose, and A EJ in a product with EK is equal to EJ BEK for all J and K going from 1 up to N. So suppose I let V be summation, I don't know, R sub J, E sub J, J goes from 1 up to N, and W is summation S sub J, E sub J, J goes from 1 up to N. E1 up to En is the basis for the vector space. Each vector is a linear combination of the basis vectors. So AV in a product with W is summation RJ EJ. J goes from 1 up to N. In a product with W, let me use K as my index of summation here. In a product with summation K goes from 1 up to N. SKEK, sorry, it's A of this. A of V in a product with W. So this is summation J goes from 1 up to N, summation K goes from 1 up to N, RJEK, RJSK times the inner product of AEJ with EK. But we just showed J and K go from 1 up to N, RJSJ. This is the same as the inner product of EJ with B of EK. And this is exactly summation RJEJ inner product with B of summation SJEK, which is V B of W. So AVW equals V BW, but B is just A transpose. So this is AVW equals V A transpose W. So if you have an n by n matrix A, and you call it transpose B, the inner product of AV with W is the same as the inner product of V with B of W. And if B, which is A transpose, is equal to A, then AV inner product with W is V inner product with AW. That's what we wanted to show. Okay. This is all basic linear algebra, which is nice to know. It's important to know. I will see, no one has any questions because no one's here. So I will say that maybe at this point I will stop. But I do have a Zoom session tonight at 7. And if you have questions and cannot be on Zoom at 7, send me an email today and I'll arrange a time where we can meet on Zoom. So you should have more than enough opportunities to ask questions about all of the material in the